We're going to start off today with the gravitational equations. You need to be able to derive these. Not all of them are on the APC test. The first equation that we start with is the one that all of these are based on. The force of gravity equals. I'm going to actually do it this way. And this is an r hat. Now, why is it a negative? If r hat points away from the planet, the force of gravity points inward. So that's why the negative. Notice we have a little m and a big M. The little m stands for a mass, a pen, your body, or, for instance, the moon around the Earth. The moon would be little m, the Earth would be big M. Which one's first, which one's second? Sometimes I write big M, little m. It doesn't really matter, actually. Okay? Then, and as we know, of course, this right here is the gravitational constant, 6.673 times 10 to the minus 11th. Most of what we're going to do in this chapter will be with variables, though. You will be expected, if asked, to calculate them. But we assume that if you have those numbers, you can put them in and get a value. Okay? The next one we need is little g. Well, since the force of gravity also equals mg, notice one of the m's cancel, and that gives us g, sorry, those are both vectors, equals negative g, big M over r squared, r hat. And once again, remembering that the gravitational field is like the wind blowing on the water. The wind could apply a force if there was a sailboat there. Likewise, here in front of my face, there's no force there, but there's a possibility for a force if I put a mass there. And it is the gravitational field acting on a mass that produces a gravitational force. Next one that we need is the potential energy. Well, we'll go over here, we'll derive it, and come back. We know that work equals the integral of force dot dx. You will find out in this chapter that we're going to be going between L, X, R, etc. But they both have the same units of meters. So in this case, I'm going to change it from dx to dr. This says, specifically, take the antiderivative of the force function where x is the only variable. And we're going to put in limits of integration. We're going to start at infinity, and we're going to come to a point r from the planet. So, I put in my force equation. Oh, that was silly. dr. And notice that all three of those are constants, and we know that constants can come out of an integral, which gives me negative g m integral from infinity to r of r to the minus 2 dr. Our rules for antiderivatives, or for integrals, add 1 to the power, subtract by the new power. So our constants again, and r to the minus 1, you see how I added 1 to the power, divide by the new power. And then we put these over here, our limits of integration, to remind ourselves that we're going to do final minus initial in a bit. Well, once again, that can come out of the equation, and a negative divided by a negative is a positive. And now we have 1 over r, then we have to put it our final minus our initial. And what does 1 over infinity approach?
0.
Basically 0. So this gives us g m over r. But we have one more step. We also know that the force equals the negative change of potential energy. That one's a positive, but the potential energy would be negative. So that's why our third equation is the potential energy equals negative g m over r, the gravitational constant, a small mass, or a satellite, big M, which is the planet or the sun, if you're talking about the planet going around the sun, and the distance from that planet. Now, if you're on the planet, like right now, my potential energy due to the Earth would be my mass, the Earth's mass, and the radius of the Earth. because that's how close I am to the center of the Earth. Okay? When you're very, 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 very far away from a planet or the sun, sometimes the radius of that celestial object is irrelevant compared to your distance. Okay? But it actually is between the two centers. Why is it negative? Hopefully we remember. Let me get rid of this. Hopefully we remember that when we had ramps, and if we have a ramp like this, if I say, oh, here's my reference point, then u equals 0, and all of this is negative. And the farther down you go, the more negative. Let's call that, negative 10 joules, negative 20 joules, negative 30 joules, etc. We all follow that, right? So the farther down the ramp you get, the more negative. Or another way to look at it is the higher up the ramp, the more positive. And isn't negative 10 more positive than negative 30? So this is positive change of potential energy, negative change of potential energy. Do we agree with that? Yes? Now, if an object were to have, let's say, we'll say that the bottom here, we'll just go to the 30. Make that easy, okay? So it takes 30 joules to get out of that ramp. If an object has some kinetic energy, it starts to roll up the ramp. But if it doesn't have 30 joules, it will not get out. And that's going to help us here in a bit. The next one. Yeah, actually that's exactly what we're talking about next. So if we were to take an object, let's say that this object is given an amount of kinetic energy. If that kinetic energy were 10 joules, it would go whoop, and go back. You have 20 joules, it goes up, it goes back. 30 joules, it goes up and it stops. If it has 31, 32, whatever, if it has more than 30 joules, it gets up the ramp and can keep going. This is the idea of a ramp, but for gravity, this reference point is at infinity. Why is that true? Well, we'd agree that as r gets bigger, the gravitational force gets smaller. Likewise, as r gets bigger, the potential energy approaches 0. Do we all agree with that? So we're going to pick this to where our reference point is 0, which is at infinity. Now, it's not 10, 20, etc. It's a lot more than that as you get closer and closer to the planet. So this would be approaching the planet, or approaching M. As you get closer to M, you have more and more negative potential energy, and as you have more negative potential energy, you need more kinetic energy to get out. And if you have just enough kinetic energy, so like here, if my potential energy here is negative U, some value, whatever it is, how much kinetic energy you need to get out? U. And notice that U plus K would equal 0, and you get out of the ramp. So that gives us our next equation. Just as before, we had our total energy before equals our total energy afterwards. And if beforehand we have kinetic energy and we have potential energy, that's going to equal 0 at the top of the ramp. Now let's put in those numbers and solve. Our kinetic energy, as always, is 1/2 mv squared. Our potential energy now, though, is g m big M over r squared equals 0. Does everybody notice the little m? It's almost as if, one more time, I can't do this because I don't have it with me, but if I were to drop a heavy object and a light object, they would hit the ground at the same time. We've done that numerous times. So with conservation of energy, the mass doesn't matter. A massive satellite or a massive rocket and a little bitty rock would need the same velocity to get out of the Earth. So let's solve for that velocity. So we're going to bring that to the other side and get rid of the m. So we have 1/2 v squared equals g big M over, oh, that's r, not r squared. Someone probably saw that, right? Okay, so now I solve for v. V equals the square root of 2gm over r, and that's our escape velocity. You will not be given this equation on the AP test. You'll be expected to derive it on your own at a moment's notice. Okay? By the way, all of these equations right here, these are all general equations. General equations mean they are true in all cases. You might say, but what other cases might there be? And that would be circular orbits. So in this case, what I'm going to derive here are the ones for circular orbits only. So let's start off with, we have an object going around a circle. Let's say that this is the Earth or any big gravitational object. That's mass m. And let's say that we have an object moving with a velocity, and it's some satellite or whatever going around, and this is a distance of r from the center of the planet. Well, from F equals ma, our force that keeps it in the circle would be the force of gravity. Equals m, and because it's in a circular orbit, v squared over r. Already we noticed that one of the v's, that the r cancels, one of the r's cancel, and one of the m's cancel. And which m cancels again? Little m, which means once again, it doesn't matter if it's a big satellite, a massive satellite, or a light satellite. We get v squared equals, one of the r's cancels, one of the m's cancels, and we get g big M over r. So let's write this, number 5. We get v, and that's circular orbit only, g m over r. Notice this was an escape velocity, and that was in a circular orbit. Let's compare them, shall we? This one has a root 2. That one doesn't. That means an object is going around in a circle, and it is in a stable circular orbit, it will have that velocity. In order to get out of that, get away from that planet and never come back, it would have to have root 2 more speed. To leave and never come back. Now you say, well, what about in between those two numbers? It would go out, it would leave its circular orbit, but it would still not escape gravity, and it would come back and it would enter an ellipse. I saved this. I didn't erase it because we need it. We know that kinetic energy always equals 1/2 mv squared. And for those people out there that might want to troll a little bit, and yes, if you go into relativistic speeds, that's not true, but we're not dealing with that here. So I have a v squared. Just going to stick it right in there. So I get my kinetic energy. And this is again for circular orbits only. Equals 1/2 g little m big M over r. We're going to compare that with this. What do we notice? That one's positive. Kinetic energy can only be positive. That checks out. We also notice, if this is u, let's imagine this were 100. It would actually be negative 100, and that would be positive 50. It would be positive and half as much. And of course, if we have your kinetic energy and we have your potential energy, we can find your total energy. My total energy, which is U plus K, will equal negative 1/2 G MM over R. Again, that's negative 1 plus 1/2 gives me negative 1/2. Now let's compare these numbers just to make this a little bit more obvious. If I had 600 joules of kinetic energy, if that's 600, then what is this? Negative 600 joules. And my potential energy would equal? Negative 1200. And negative 1200 plus 600 gives me negative 600. And you might say, what does this mean that E is negative? Once again, imagine our ramp. An object has kinetic energy. Let's say it has. Well, since we're using those numbers. And here at infinity, U equals 0. Let's say right now, U equals negative 1200. It's going to race up and use up its 600 joules, won't it?
See.
And how much will be left over at the top? No kinetic energy, but there will be, it'll be negative 600 joules of potential energy still. And if you've used up your kinetic, then that must be your total energy as well. This is where V equals 0 and K equals 0. But you're saying, but here it's exactly a half. Well, here it may be in a circular, it's in a circular orbit. There it's not in a circular orbit anymore. Okay, this is valid only for circular orbits. Those are the kind of details that you must remember. And now we get to the last one. This is the one that takes students a little bit longer to figure out. Let's go back to our Newton's, let's go back to Newton's second law. And let's say we have an object in a circular orbit again, and make it easy, we'll say that's M, that's R, and it's moving with a velocity V, and it has a mass of little m. Well, my force that holds it there is gravity. So we have big G, big M over R squared equals M V squared over R, and you'll all say, we've done this already. All right, well, let's simplify. We get rid of the M's, we get rid of one of the R's, and we get G. M over R equals V squared. But you know, V also has another basic definition.
How come you keep on not including the negative on the force?
Because in this case, we're using magnitudes.
Oh, okay.
Remember that when we did circular, great question. When we do circular motion, remember that positive is to the center of the circle?
Oh, so it's always going to be positive.
Yeah,
Okay.
for circular motion.
Yes.
When we wrote that equation, if you want to use it as a vector and decide the direction of the gravitational force, R points outward in all directions. Did we talk about that or not?
Yes.
R is an outward direction, and the force is inward. That's why it's negative.
Okay.
And also, just by the way, when doing this calculation to get that negative, you got to have that negative or the calculus doesn't work right. You end up missing a negative someplace, which is always very disturbing for me, because then I'm looking for this negative everywhere. All right, so it's been a serious lecture up to that point, but you knew it was coming. Yeah. Okay, so we also know that speed equals distance divided by time. Yeah, so now that we've lost it. And our distance around this circle would be what? In one circle, how far around do you go? Circumference, 2 pi r. And we're going to call that time for one rotation, big T, the period. Plug them in. Yeah, I thought it too. That's 4 pi squared, r squared over T. I'm going to bring, sorry, T squared. That would have been better. I'm going to bring the T squareds over here and the r squareds over here, and we get and this is known as Kepler's third law. Yeah, crazy law, crazy guy Kepler. Now, this Kepler's third law, let's identify a few things. What do you see is conspicuously missing? Again, little m is not there. That means if we have our same circular orbit here around big M. What was that? So let's say that we have same R and we have a small m here, and this one says 4m. So we have a big satellite and a small satellite. Their periods will be the same because they're around the same planet. That's obviously a constant, constant, constant. Same radius, In other words, it's same radius is another way to say same circular orbit. If everything else is the same, then the time for it to go around will be the same. This mass, a lot of people would think that the smaller one will be faster. No, they will never catch each other as long as they're in that circular orbit. They would need to have a rocket that would speed them up. Now, you might think if they speed up, what would happen? Well, if they speed up, they couldn't stay in that orbit without other rockets maintaining them at the same distance from the Earth. Because, look over here, if you have more kinetic energy, then your radius must get smaller. Well, look up here. As the radius goes up, the velocity goes down. That's why, again, Mercury goes very quick around the sun, small orbit. The Jupiter goes very slowly around the sun, greater orbit. And again, you can imagine that. You take a rope, you're going like this with a rope, and you pull it in and start speeding up because you're closer to the center. So, now we have these 8 equations. These are the equations that you will need to know for this chapter. Obviously, we will practice with them, etc. But on the AP test, you get this one. I'm not sure if this one's on the equation sheet. We can look at it. I believe we have this one as well, etc. The rest of these you are responsible for. And since I've given you a worksheet, and we've now gone through this, you're expected to be able to do this on your own.